Yeah, so we'll go ahead and kick things off here. So I'm Mark Weller. So I'm in the education department here at EV West. And so this is kind of our experimental, our Carts and Coffee. And so really so we have an agenda. We want to go through a variety of things that we can use as educators to help teach students about EVs and engage students in learning and working on EVs. So as I've been in cars all my life, and so I currently, I've been teaching at the college level for the last 20 years. So I've seen a lot, done a lot in automotive. I was a smog technician for 20 years. Whenever I went all EV, let my smog license go. And so now I'm just doing EVs. Still do teach gas when necessary. I have a gas class going on right now and an EV class. Yeah, so we just want to spend the next 3 hours or so just sharing ideas, really. And we want to get some feedback from you guys out from here in our live audience and out in cyber world there. So please send your comment in the chat box there and any ideas or anything that you want to see. We want to make it a fun time here. We will take a couple breaks. So we're thinking we'll go. Maybe have 2 breaks, so it runs from 9 to 12 Pacific time, and yeah. And
as Mark said, he's the educator. I'm Michael Bream. I'm from EV West. We are an electric vehicle parts supplier, and we've been working with Mark Weller over the past couple years to develop an educational cart. So this is the result of our work, and the impetus for the project for him was he had an automotive class and he tried to bring in some other training materials for the EV space. And he came on our radar when he reached out to EV West and basically said, I can't get any of this stuff working. I don't really understand it. It doesn't come with enough support. And he was stuck as an educator. He used valuable resources and money from his department and really didn't get anything in return for his students. So when he reached out to us and told us what he was looking for, just a very, very simple basic system that would fit on an ADA compliant cart, at first we kind of thought, well, that's crazy. You can't drive a cart. It doesn't make much sense. But we started talking more and I, getting his background as an educator and his insight from his perspective, we realized, yeah, you really do need a cart. We need this system that we can teach people all of the componentry and the specifics about it, but in a setting, in an environment that's a little bit more friendly than being out in the garage with an automobile that can actually drive and potentially be dangerous and whatnot. So what we wanted to do is just kind of further this. We've kind of taken the cart and the features. Mark has formed some really nice curriculum around the cart. So there's all this curriculum, and they give exercises, things that the students can do within the curriculum. And today we just wanted to share some of those exercises with you, some of the things and exercises that you can go through on the cart with your students. But we also just wanted to reach out and start kind of fostering and talking to this community of EV instructors. It's not lost on us that this is new. 10 years ago, 15 years ago, there weren't mass-produced EVs in the American market, and largely those were serviced, initially by manufacturers because they were all under warranty. But we're just now getting into this era where we've got, over 1 million EVs that are aging in America and coming off warranty, and there's going to be a huge demand for electric vehicle automotive technicians coming up just because there aren't any there now. And we need to fill this space. So instructors like Mark are seeing more and more students reach out, more and more companies reaching out, trying to get information on where they can get, where does this workforce come from? Where do we get an educated workforce for electric vehicles? And really, this is the answer. The start of it is right here. You start them on something like this, you get them on a cart. The cart is here to teach, the most basic systems. When we talk about combustion engines as a reference, all of us understand the 4-cycle, of an engine. We understand compression and combustion and all of that. But when it comes to an electric vehicle system, a lot of us just don't have the basics down. And so that's one of the neat things that the curriculum that Mark's developed and the cart kind of go hand in hand to give all of your students that really, really good foundational knowledge that then they could go in and expand on that, especially with something proprietary, like a proprietary propulsion system or a battery system or something like that from a major manufacturer. And they're not missing that foundational knowledge that they would have with a combustion engine. So that's the point of the cart, and that's why we're here. And we want to improve the product. We want to improve our communication with the community. And that's the purpose of Carts and Coffee today. So we'll be your hosts. We're happy to have you guys. I'm going to turn it back over to Mark, and I think you're going to get right into some demonstrations on the cart, right?
So, the EVs, they're not that much different than just a regular gas car. So the car itself is going to be just the same car that we've worked on for years, right? You're still going to have a 12-volt system. And so I like to break it down for the students. We've got the big three. So you've got the electric motor is on the bottom here, and then you're going to have your battery pack, which is basically your fuel, and then you're going to have your inverter. Okay, so all EVs are going to have those components, and then we're going to have a couple other pieces. We're going to have the charger, okay, and then the DC is here. Oh, are you moving me with the camera over there? Oh, okay, I see how you did it there. Okay, very good. All right, and then, so I guess while we have that on that display there, so you're going to have some high voltage fuses here, and then all the EVs or hybrids are going to have a contactor, which is essentially going to be a heavy duty on-off switch. And so really that covers the main pieces. So you've got the dash here, but there's really nothing magical about the dash. That's going to be the same as on any gas vehicle. So all EVs are going to have an electric throttle, but really all gas cars now, they have an electric throttle as well. So there's really not anything different there either. So that, I believe, covers the main. So the battery that's definitely one of the bigger concerns that people have. And the reality is that is still kind of the most fragile piece to the puzzle. It is still kind of the most expensive. But it has gotten definitely much better, and these are quite, these have been very reliable, really. Not a whole lot of issues with them. So we do have, Michael's going to talk in a little bit here on the battery management. So that those are, we've come a long way in keeping the battery protected and getting longevity out of the battery. So so those are your main pieces. The question was, for high school educators, they're getting some, I guess, pushback from the administration, or concerns from the administration on the safety. How do we keep our students safe when they're working on electric vehicles? And so,
keep them away from gasoline.
Oh, wait, we had it. What was it, Michael?
I said keep them away from gasoline.
Oh,
that seems to be more
right,
dangerous. It seems to be, a liquid. It can flow around.
Yeah, so
from
my experience, I would submit that the EVs aren't any more dangerous than gas.
So I think the most important thing, right? The answer to that question is, with knowledge comes safety, right? If you don't know how to handle fire, you're going to get burned. If you have knowledge, you can use fire as a very useful tool. The EVs are in that same kind of range. And unfortunately, and this is the reason, this is the impetus for all this, is we want to educate people. The first time I saw an electric car go in for service, it was a 2012 Nissan Leaf. In the Nissan manual, the first step is to put a barrier fence around your post lift, right? I take offense to that, and I take offense to that because they're not educating anyone. They're simply using almost like a scare tactic, that this is so dangerous you need to be away from it, right? When the reality is, these high voltage packs aren't that harmful for humans. They can be harmful for tools, and there's a lot of ways that people can get injured, but not in the ways that most people think, right? So we want to kind of demystify some of those myths about the electricity, and especially these isolated DC systems that we're working on. These are not wall systems, right? And there's this thought that you could get electrocuted or go through earth ground, or you can't be doing this stuff when you're barefoot or standing in water and all that. And none of that stuff's true. And that's the purpose of the cart, is to teach the students this, but actually show them where the dangers exist and where they don't exist, right? And that's the only way you're going to be safer. You can't put barriers around everything and then call it safety, because they don't understand the consequences. So with this, the result is you'll have students that can safely go into a system, look for the particular components, manual safety disconnects and shutdowns, be able to disable the system, and then use their own diagnostic equipment, such as voltmeters and readers and scanners, to actually test the components to make sure that they're then safe for humans to go in and actually touch. And there's a series there, We do this all the time with combustion engines. If you're going to work on, say, exhaust headers on a car, one of the first things you do is you just kind of wave your hand near it. Right? Yeah, we got talking like somebody who's burned themselves. But yeah, you kind of just, and then maybe touch it with your finger, and you're like, okay, that nut's safe, and then you get a socket on it and you start removing it. But that wasn't your instinct. You didn't come in and work on that exhaust manifold and that was your instinct. You got there because somebody taught you that. Or you learned on your own, right? You burned yourself and then learned on your own. But most likely you went through a program, like an auto shop program, and they taught you those little tricks and tips. And that's what this is here for, teaching the little tricks and the tips and the easy way to get around an electric vehicle without getting shocked. So now that being said, we do teach a couple classes on building the cars, and we offer the students the opportunity to come up and feel what it feels like to get shocked from a 120 volt EV system and a 400 volt EV system. And you'd be surprised, it's just a tickle. But it's nice to know, because I think the most important thing is we're fighting a long established industry, right? This is threatening to certain industries. There's people that generations have been involved in these industries that electric vehicles now threaten, right? So there's a lot of misinformation, and there's a huge push of information coming from these other industries that are trying to discredit this. And it's easier for them to do because there's a lack of general information, there's a lack of general knowledge about these systems. That's really what we want to get around, so that the common person now is like, no, these are much better because of this, this, and this, and they've got solid foundational reasons for that. Yeah. So when you fully understand the electric vehicle, you will at that point then understand that it's almost crazy that we allow students to work on combustion engines in shops. It really is, with all the cancerous materials, fluids, I mean, not just fire hazard, but literally combustion hazards. I mean, on and on and on, and none of that stuff really exists with the EVs. And at the same time, we're always hearing stories about people getting injured. I mean, Jay Leno just the other day got his face burned working on a gas car, right? We've looked, Mark and I the other day went through every news article we could find on the internet. We're still waiting for that news article of the EV technician getting injured. Now there's less EVs, so statistically it's going to be tougher to hear those stories, but we really want to be factual here. We want, okay, what happened? How did they get injured? What was it? How can we prevent this? The more that we understand about these things, the more we can, prevent future occurrences. So causation is really important to us. But I think what we find is a lot of these stories that are out there circulating about EVs tend to just be kind of propaganda stories against them with no real significant facts or details that help to further the education on the systems. So as far as safety, The cart, has a lot of safety measures built in. All of the live joints, this is open right now for viewing and for diagnostics, but students can get to that point. They can work with the cart where it's completely insulated, and we call it the little finger test. You try and put your finger in anywhere and touch conductive surfaces, and you can't. But then as the students educate themselves and they get past the first couple chapters of the curriculum on safety, then you can start doing things like removing the lid on the contactor box, getting into live connections, actually going in with your multimeter tool, inspecting fuses and things like that, because you've done the right steps and that that you're, shut down electrically in the junction boxes, but you also know diagnostically you have the meters and you know how to test your meters and you can trust them as well. One of the things Mark and I have kind of found out through the course of the class is there's a lot of people that just don't understand the tools, like a regular multimeter, and that's something that we teach a lot of skills, and those skills are also in the curriculum of using your meter, not just going in and testing the voltage, but having a technique where you can test a known voltage, test your unknown voltage, and go back to your known voltage. And that way you have an absolute 100% certainty that what you're reading on the meter is accurate, right? Because the meter can make a mistake, humans can make a mistake. We've seen students plug the leads into the wrong port on a meter, get the wrong reading. So we teach in the curriculum a way of actually verifying that the meter works with a known voltage and then going to your unknown voltage. So there's a lot of these little trips and tips and tricks and stuff like that we have in the industry that just aren't well known outside the industry. We want to make those more common. I mean, it's our goal to make it as common as the common person's knowledge of a gas engine, right? Even my mom knows so much more about how a gas engine works in an electric vehicle. It's pretty insane because she's never worked on a gas car, but she's just been around that knowledge. So the gentleman's question was, why are the manufacturers and the OEMs so concerned about safety to the point that they're reluctant to train certain aspects of that? Is that what I'm understanding the question to be? My answer would be speculative, that it's based on liability. Nobody wants to see anybody injured, and generally responsibility flows uphill, right, towards the manufacturer. So even if it's a big manufacturer like a GM or a Ford or something like that, and it happened at a local service center, ultimately the manufacturer tends to bear the responsibility for stuff like that. And I think that most people want an abundance of caution. Mark and I try and strive for that, having this abundance of caution and just making sure that everyone's really safe. We teach things, a classic example is we teach a lot of things like as far as gloves and protection like that, but when you actually go out into the real world and see actual technicians working on this, like go into a Tesla facility, right? Or another manufacturer that's making it, you will not see them wearing this gear. So you kind of have that duplicity where they're kind of saying one thing, do as I say, not as I do. But I think what we're seeing is that the actual technicians working on these cars have their own comfort factor because they now understand this stuff, right? When you come up to a raw bus bar and you don't know if there's 400 volts on it or how you should approach it or how you go about shutting it down, there's a lot of anxiety and fear and trepidation in that, right? But if you completely understand that system and you know that you've shut it down properly, you can then go in with confidence and work on it. And that's what we're really trying to build, is that confidence in safety. It's not, we can't be safe by saying, wear eyeglasses, wear gloves. Okay, that's the end of the safety speech, right? It's really like a way that you think about things and go into them and understand and approach them. Yeah. So, but yeah, that's a good question. I really don't understand the main answer, other than in America we tend to be a little bit litigious and kind of push liability and responsibility on others, even if we didn't do everything that we were supposed to do. Yeah.
Can I just jump in for a sec? On the as an educator, I'm Mr. G from New Jersey, and I have an analogy for the safety. Just simply put, I teach welding as well. So if you think about welding, I would not let anyone just walk up to the welder and the welder machine's on. I would say, whoa, whoa, whoa. I would say, whoa, do you know what you're doing? But once I've taught someone, I can teach a freshman in high school how to weld. It's a similar risk factor because you have high amperage DC, and the wires are just loose. You could just touch them in your hand. So why am I comfortable teaching welding, and I've done it for years, is that there's a certain amount of procedure to it. You know, you got to know where the problems are, but you're not going to just let anybody do it, right? So you can't let someone walk up to a hot stove, and you can't let someone walk up to a welder that's on, and you can't let someone just walk up and start touching all the leads on an EV. But once they have some training and they understand the like what's involved, positive, negative, where the energy flows, connections, good connections, bad connections, then just like your kitchen, like basically, would you let your kids cook you breakfast if they've never used the stove before? No, you'd show them first. Look, the stove is hot. Check it out. This is what goes on. You know, so there's a procedure to it. But once they're comfortable, I do let my freshmen weld. You know, in the booth, I walk out of the booth. I let them do stuff, and the same with the EVs. Once they understand the roadmap, there's a map to the electricity. It's not like random, and it's not like a cartoon where you get near it and it makes you jiggle. You know, like there's a roadmap and there's a procedure. So, you know, I would say I think you can have EVs in an educational environment, and the earlier you start the kids, the better. And this cart has basically a floating electric vehicle sitting right on there. So it's got everything that an EV would have. So yeah, that's my 2 cents on it. As an educator who's currently doing this, pun intended, right? Anyways, there you go.
That's great. We had a gentleman ask a question about first responders, and generally some first responders are giving pushback to electric cars because there's not a standardization in shutting these down. And again, oh man, this is just another classic example of why we need education like this. Every manufactured car in the United States that has an SRS airbag system will disconnect the battery upon tripping that system, right? So first off, these first responders are going up to these cars that are disabled anyways, right? The pyrotechnic fuse came out in about 2014. We started seeing widespread adoption in 2015 and 2016. And now every new electric car in America comes with a pyrotechnic fuse that can be triggered to open that fuse the same way an airbag is triggered. It's a little ballistics charge. So nowadays, you know, could you imagine being a first responder and having to read the Kia manual and the GM manual and the Ford manual and the Tesla manual? So this is just kind of a leftover misinformation, right? If you see first responders reacting to any sort of incident with an EV now, they're not running around trying to find these plugs and whatnot. They're actually just trying to, you know, pay attention to the human life, right, and rescue them. So that's the neat thing about technology, right? These systems are very complex, they're very smart and very capable, and so they do actually shut themselves down in a wreck that would be of any significant forces that could expose any of these systems. Of course, you know, minor, you know, bumper, you know, taps and small wrecks and things like that, fender benders and stuff like that, they're not going to be affected because you would literally need to expose the system. Right, and we're constantly reminded in the news and the media about similar accidents with combustion vehicles, and once that gasoline catches on fire, it's really, really tough to extract the occupants from the vehicle, right? Electric vehicles do have a fire hazard, but it's not a combustible fire hazard. It's one that's done through short circuits and heat that generally take time for that to happen, right? And again, now that we have these safety systems that are tied into the SRS and the airbag systems, a lot of that instantly just gets disconnected upon an accident. So it's a really good question. So I think for now, you know, it'd be interesting to have those kinds of talks with first responders and see if they're up to date on the latest information. These cars do actually shut themselves down.
So the BMS is going to be your battery management system, and so on the a lot of things kind of started from the Toyota Prius and the Honda Insight back in the day. And so they had a BMS, which was a battery monitoring system. But all it did was just look at the cell voltages, and if anything got too out of kilter, then you would get the orange triangle of death, and then you would need to go in and service your high voltage pack. So when we got into lithium, then they do have an element of how would you say it gently, flammability element there. And so we need to not only monitor the cell voltages, but we need to manage them, because we don't want the cell voltages of any individual cell to go over its maximum rated limit, or realistically it can potentially catch on fire. So there you'll have the BMS so the battery management, where it's actually going to watch the cell voltage, and then if it's not happy with that, then it's going to take corrective action to try and bring that voltage down. And then if it's not able to bring the voltage down, then it will, if it's charging, it will shut off the charger, or you'll get the basically a check engine light where you get the orange triangle of death. And
so, what Mark's going to do is going to pull up a serial communication tool that's going to communicate with our onboard system. And what this tool will allow us to do is to look at the actual architecture of our battery pack, right? We'll be able to look at how many cells we have in series, what the individual voltages of those cells are, and what the collective voltage of those cells are. We can also look at the difference in voltage between the cells, commonly known as the balance of the pack. And we're also going to look at the temperatures, because we can monitor the internal temperatures of the battery pack and make sure it's at a safe operating temperature. That's okay, I'll just kind of narrate what we're doing. So he's got his menu online here, and he's now logged in to the system, right? And so this is an actual exercise that students can do in class, where it's not a simulation, they're actually communicating directly to the battery management system on the pack. So one of the first things Mark's going to do is issue a command to show the pack voltages. So now if you look at the screen, we can actually look at the individual voltages of these cell groups that are inside this pack, right? And the architecture of this pack, it's a Tesla battery, so we've got 74 cells in parallel, and that sum voltage of those parallel cells are represented as each individual cell group. And then of those groups, we have 24 of those groups in series, which gives us roughly a 100-volt battery.
That's not, are we on that camera?
So with the BMS, since it's our manager, we task the BMS with telling us what's safe and what's not safe and what the limits are. So these can be entered by us, right? So we can go in, we can look at a manufacturer's spec sheet for, say, the maximum temperature of a battery. We can then enter that, so the system will give us a warning if we're approaching the maximum temperature of the battery, or we can alter it. So in a lot of times we'll have exercises where we do demonstrations or simulations of actual fault events. We've got, we're going to do a little bit of that later on. But that's one of those cases where you could set an artificially low temperature on the battery and then exceed that and actually trigger a real fault event on the system. So the question was, will a regular scan tool work on an electric vehicle? And the answer is a little bit more complicated than a yes or no. The reason is, as you technicians know, and future technicians, we have a system called OBD2 for Onboard Diagnostics 2.0. This is a requirement on all cars because it was to make, of course, the job easier of finding a fault with the vehicle, but also making it more affordable for consumers. Consumers were going in and having to pay for all of this diagnostic work, when in reality the computer was simple enough to tell the story. Unfortunately, most of the stuff was centered around emissions. So because of that, when electric vehicles came out, OBD2 was not mandated on electric vehicles. This is kind of a funny little fact that most people don't know. So the EV manufacturers are kind of up to their own devices for diagnostic plugs, and several of them do use the actual OBD2 plug, and they give some codes. But by and large, OBD2 is mostly used for combustion. When you go in there, most of the information that they're going to give you is all the details. You know, if you look at all the things that can go wrong in a combustion system, you start to look at an EV system with whole new eyes. You're like, wow, this is actually very simple compared to the complexities of just, say, you know, a fuel injection system, right? And the complexities and timing of that. So, you know, so the short answer is no, you're not typically going to get those same OBD codes in scan tools. And I think the real answer is what happens is we get more and more specialty companies like Pico here that make scan tools that are more specifically designed for electric vehicles. They focus on CAN bus and high voltage systems and isolation checking and things like that. So, yeah, so that's, I think, one of the other reasons that this cart exists. You know, if you could just take your existing scan tool that you've been working with for 20 years and you're really comfortable, and then all of a sudden you can just work with that on an EV, it would be a much easier transition. But since those tools don't work, again, there's the need for kind of learning this new approach to these systems, learning the new tools that we have at our disposal, and actually how to work and diagnose the systems. Okay.
Yeah, and kind of from what I've found in industry and working with this, so manufacturers that have built gas vehicles and already have an OBD2 plug.
Yeah.
Like, so basically the General
Right.
Motors, the Fords, they're currently using that.
Yeah.
But like Tesla, well, it was interesting. Tesla for a few years they had the plug, but it didn't work like as designed.
Yeah.
But so Tesla does not use the standard 16-pin OBD2 plug. They're just using, well, they had a variety of things. But there are aftermarket tools. Autel does a pretty good job of, they have where they can integrate with, basically you jump into the existing Tesla harness and they have an adapter and then you plug into that. So there are some really some cool features out there. And,
Yeah,
and
yeah.
some neat things where you can, with some of the aftermarket scan tools, where you can talk to just the battery pack outside the vehicle, which is really cool. Like, it has worked
Yeah.
fantastic for us,
Yeah.
actually. Yeah. But so there are some options, but there are really not any standardization or there's no standardized codes for sure on with regard to the battery pack. So
Yeah, mostly proprietary tools is what we're finding. And that's true with other manufacturers, right? You know, you go and work on a BMW with off-the-counter scan tool from the auto parts store, and you're going to get all the codes that are required by law and regulation, but you're not going to get the proprietary codes that BMW and these other manufacturers kind of keep you locked out of, right? And so the same, you know, you can go out and buy the expensive tool, and then you can scan a brand new BMW and get, you know, kind of all the minutia detail and all the codes and everything like that. The same is very much true for EVs. There's a lot of specialty parts and tools. Your regular, typical scanners aren't going to be able to scan a proprietary battery pack from Tesla and give you the status of that condition, right? There are tools that do that, but keep in mind, once you get given that information, it's the knowledge and the experience of the technician that can translate that information into action. So in other words, if I just gave you 8 numbers for compression readings on 8 cylinders in a V8 engine, right? So I used a tool now, and I've gathered my information, but that information doesn't really it doesn't hold value unless I have knowledge and experience with that information. So if I have experience and I understand the numbers, I might be able to tell you, hey, we're going to have to do a valve job. Number 4 is leaking down pretty bad. It's probably a bad fitting valve seal, or whatever it might be, right? And so that's kind of the point of this course is we're not going to teach you exactly how to use this piece of equipment here from a proprietary manufacturer, but what we'll do in general and what the cart does in general is it gives you a really, really good idea of what makes a battery pack healthy and what makes a battery pack unhealthy. And if we give you the tools like this equipment here to look at the battery, take a peek inside the battery management system, we can then take that information and decipher it, right? And come up with an actionable plan like, hey, the battery should be pulled and taken a look at, or maybe we can just more aggressively balance it out, recondition it, and keep going forward. But those sorts of decisions will be based on the information that the battery management system provides. Yeah, so the question was, how does the diagnostic tool... yeah. So we are wired. It's a wired connection, and it is serial. So it's a universal serial bus, USB.
Does it need any special software, or is that just like a...
It does not. It uses terminal communication. So every Macintosh, every Windows PC, and every Linux computer comes by default with a terminal window program in it. Yeah. Yeah. So literally no proprietary software whatsoever. Yeah, and and we're aware of that. And in this package that we sell, we've got some displays and some things on it that have some proprietary componentry, but all of that stuff the software is free and it's open. It's not something that you have to charge for. So it's kind of neat because we've had actually some customers download some of that software and go home and play with the software and understand it before they have actually gotten their car up and running. So they kind of preemptively gave themselves that education. So on day one, when they turn on their car, they can kind of understand some of the information that they're getting out of their battery management system. Yeah, great question. Thanks. I think it should be noted that several companies in the EV space do operate this way. They've got pay-for-use software and subscriptions and stuff like that. It's worth mentioning that the components on this cart and that we use in the shop have been sought out to not have these subscriptions or these extra costs associated. We were previously using a drive system that required a $600 tool just to program the throttle pedal and calibrate the throttle pedal. It was pretty insane, actually. We would just loan it out to people because we couldn't look at somebody with a straight face saying you had to spend $600 to calibrate a throttle pedal. So now, when we have our BMS, the system that we chose, that we sell, can be completely controlled with free software, basically open source software. And to us, that's the single most important thing, is that there's not this like large barrier to entry into the market of all this diagnostic tools and stuff like that, like there really is with a combustion mechanic. If you wanted to go out and be a mechanic nowadays, before you can even wrench on a car, you've got to spend a lot of money on these tools and stuff like that. So anywhere that we can reduce that and just keep an old laptop around, none of these software packages are very powerful, so you don't need a lot of memory or a lot of processor speed. I think most of us guys in the shop use like $99 laptops that were on sale or something like that, because you're not doing graphics, you're not doing gaming. It's the lightest lifting duty that a PC can do, just basically sending some information back and forth and displaying it. So that's, to us, that's a real neat feature, that you can get into this and really get into the diagnostic detail and the fault codes and all of that without spending any money, just taking a regular computer that you already have and hooking it up with a cable and processing that data. So it's very, very big benefit. And so the question was basically around acquiring the software, that there's a concern and there's actually a real world danger of viruses and bad software being downloaded. So the fact that these systems operate on their own, and the neat thing is nothing is cloud connected, right? We hear more and more about that, and it's all fine and dandy until our server goes offline and then you're left stranded. The neat thing about this is the laptops that run the software and all of this stuff, it does not require the internet, it doesn't require a subscription, it doesn't require a security key. In some of the software that we're going to be playing with a little bit later in the demonstration, you can go straight back to your office, download that software, and start using it and seeing some of the issues or the easy use with the software, and get to learn it. So it's kind of neat that you can get into that without paying money or having a commitment or signing up for some big account or something like that. You can simply play with the software and get a feel for it and see if you like it. So let's finish up on the battery management system.
Okay, so what we're looking at, so we've got all of our individual cells here. So this here, what you're seeing on the overhead, we're connected to the laptop, where we're directly communicating with the battery management computer. But then at the same time, over here on the display, so this would be the driver display, and this would be typical in basically a gas or electric car now, where you kind of have your center display, touch screen or however. And so this one, we're looking at all of our individual cell voltages that the driver would see, and then at the same time that we're actually reading the exact same thing in two different places here. So we're really making it accessible to be able to see, basically watch the health of the battery at any given point there. So, okay, perfect. There we go. Using our technology here. It's nice having a couple hands here. Like,
Yeah.
this is
So, jumping ahead a little bit, one of the neat things, we wanted to build a cart that gave really fun, exciting things for the students to do, right? And talking about data like this, it might be exciting for guys like Mark and I, but we understand for the students, this is pretty boring stuff, right? Because we're just processing data. But we wanted to do it in a way that made that data fun, right? So we partnered with AEM and we used their displays to process our CAN bus data. We like them because you can introduce logic to it. So you can say things like, if this value is greater than this, then do this event or do this. And it's a true, I don't know if you guys understand the term, I've heard it before, WYSIWYG, right? It's a very, very famous acronym. It stands for what you see is what you get. It's a design approach that they took back in the day where you have these layout systems where you're laying out your different components and graphic components, and that's exactly what you see on the display. And so the AEM Dash Design software that comes with the cart is a WYSIWYG platform. So you lay the components out on the screen where you want them and can display them. Why is this important? Well, because it's a fun exercise for kids, right? If we don't make the cart fun for them to learn on, they're going to get bored, right? But we show them the connection between the raw data that the system is reading and using for logical decisions, like, is the voltage too low? Is the temperature too high? We can take those real logic binary things and translate them, go into our AEM here. And do we have this on camera at this point? Can you?
it's on right now.
Yeah, okay. So you can see we designed this in-house. We made some graphical pictures of the actual battery modules on there, did a representation of the temperatures on the display, and kind of laid it out in a way that was fun. We were kind of playing around last night with some different graphical layouts that we could do for the kids, and nowadays the electric motorcycles are really popular with the kids. So we put a screen on here for the electric motorcycles, and very quickly, I'll show you later on how it's done, but you can just put these elements in there because they're all predefined in our information package. So all the CAN variables are all that in there, and then we can put this display up. We have live voltage, live amperage, RPM, positive and negative current, and regen going back into the motor. So it's kind of neat. It's something where you excite the students because you get the students really excited about reading, this is kind of tough, right? But if they can take this and then do something fun with that information and process it, but still give them learning material where they have logic. Like in this case, we're reading the current, and if it's positive current, it's green, and then if it's negative and it goes into regen, it turns red. So we just used a simple Boolean statement there to see if the value is positive or negative, and then simply switch the color of the text. There's a lot of features like that you can do, and a lot of functionality packed into this that can make the learning process really fun for the students. So the question was, is the display a tablet, right, and essentially a software tool, or is it just a display device? So it is just a display device, except for when you're doing the software on the back end, it has VCU capabilities, vehicle control unit capabilities. And this is what gets me up in the morning. Believe it or not, I love playing with this stuff because you can sit down, you can write rules, you can write Boolean rules, and you can do math, right? So for example, a watt is a unit of power, like a horsepower, right? And you measure watts by taking your voltage and multiplying it by your current. So in the AEM software, if you wanted to give a real-time calculation of horsepower, actual horsepower, you could just simply take the data value of your volts, multiply it by the data value of your amps, and that's going to give you watts. You divide that by 746 watts for every 1 horsepower, and now you've just done a real-time conversion, and you can put that on the screen. You can even do fun stuff, like if I exceed 200 horsepower, put a picture of a horse up there on the screen. Mark was asking for me to do these little graphical things, and Chase, we didn't really have time for the class, but you can do a lot of that neat stuff with this display, and there's a lot of those exercises, I think, that really tap into the creativity of kids. We've had kids do things and see them create some things on the AEM display that we wouldn't have thought of doing, and it's really refreshing to see that kind of like open, thought. So to me, that's the most exciting thing. It really is just displaying the information, but at the same time, it has a very powerful VCU component that allows us to set limits. So we could set a flag if our voltage ever dipped below 90 seconds or 90 volts or something like that. We could put additional parameters, like it's got to go below 90 volts for a certain amount of time, or only if the temperature's cold. So there's a lot of things like that that you can program into these systems. Conversely, in the combustion world, a similar experiment or exercise for the students would be turning on an oil pressure warning system, but also disabling it, say, if you're below 1,000 RPM, because an oil pump doesn't really work well there. So you can do little things like that that are the same in the combustion world, take those same kind of lessons and push them into Boolean logic for the EV world of certain conditions that might be safe or unsafe, program those into the AEM. Yeah. So it's really neat. It's a neat way to take a look at all the raw data that's coming out of the system, process that data, and then actually just display it in a way that students like to see things, right? Gives them a lot of creativity. That's what we like.
So your electric vehicle or a hybrid vehicle is going to have a 12-volt battery just like any other car. And it's interesting, I find, that people, they get concerned about the high voltage battery. But in actuality, the 12-volt battery, you'll replace the 12-volt battery in an electric car or a hybrid car many, many more times than you will the high voltage battery. So one of the concerns will be, a car will get brought in for service, or a call that my car won't power up. And so, and usually the more common thing is it's just going to be a flat 12-volt battery. So we're going to use the DC-DC converter to charge up the 12-volt battery. Most 12-volt batteries are just a regular lead-acid battery, although there is kind of a shift from that to where we're going to the lithium. We're using lithium for the 12-volt battery, and that's something that we're looking at here as well. So really all we're doing is we're just robbing voltage from the high voltage battery. So in this case here, it's 100 volts DC. So we're just going to take that 100 volts and we're going to drop it down through a buck converter and drop it down to 14 volts to charge our 12-volt battery, which is actually, we won't be able to see it on the camera here very easily. Actually, let me see if I can do this here.
It's just a 12-volt battery.
Yeah. So, okay. All right. So it's actually underneath here, but so let's go ahead and do some testing. And so it's going to be just similar testing to how you would do just your alternator. And really, in simplest terms, it's just, let's see if it's coming through on the camera. Actually, it's not quite coming through on the camera. Let me fix this here. Let's do this like this here. And let's go this way. That's going to be amazing. Okay, so all right, so we're talking about this piece here, and so you just have high voltage DC coming in here, and then you have your low voltage DC coming out on the other side here, and so we're just tapped in on the high voltage over here in our junction box. So it is fused. So on this one here, so it's going to be this one here where we have a 15 amp high voltage fuse, and then. Let's see, so from there, so let's go ahead and do some testing. Let me see if I can get the meter up here and how that's going to go. Drew, you may need to help me with that, or Michael. Let's see, is that going to show up on there? So I'm just going to go to my DC volts here.
Is that just a standard multimeter?
Yeah, it's a standard multimeter.
This is a Cat 3 meter, so it is rated for high voltage. It functions the same as a regular voltmeter, but it is rated for the higher voltage. So that's definitely, so for your automotive program, you'll want to have, it's not just your regular cheap, I don't want to call out brand names, but it is, and this is a fluke here. We like this one, but it can be, there's tons of companies that make them, but it does need to be Cat 3 rated. For the high voltage.
So the exercise here is to understand energy, right? And what we're taking is we're taking a high voltage battery, right? Typically from 100 to 400 volts. And we're using the energy from that battery to charge our 12 volt battery, right? But because of the voltage and the extra power, because power is the sum of volts and amps, right? We have so much more power in the high voltage battery. So to bring that down to this level, we're going to dramatically reduce the amount of current that's needed on the high voltage side and increase the current on this side. So, and it's a direct linear relationship. So if our main high voltage battery is 120 volts and we're charging at 12 volts, every 10 amps out of our DC converter only requires 1 amp from our big battery, right? So a very, very powerful 12 volt system would be somewhere in the order of 50 to 100 amps, right? You're talking maybe an off-road winch or off-road lights or a stereo system, a lot of electricity being used in the car. That same 50 to 100 amps from here is only 5 to 10 amps from your high voltage battery. It could be run on the smallest of cables, right? And so that's why this is very relative, even to combustion cars, because we're seeing this now is materials become more expensive, especially copper. We're seeing more and more manufacturers go to 48 volt systems. Now they've got 4 times the power in that house battery, and they can reduce the cross-sectional diameter of their copper, right? They can reduce that, reduce the weight, and improve the efficiency of the vehicle, and also reduce the cost of the vehicle, of the raw materials. So a lot of this stuff with the DC converter and the translating of voltages and stuff like that, you'll see a lot of that stuff sneaking into combustion cars, but the technology was born right here in EVs first, right? And this is where they kind of figured it out on EVs, and they're like, wait a minute, that would work good in the pickup truck too. And so we're just now starting to see that. So this is kind of neat. It gives them a handle on the math and the calculations, and you should know, converting from one voltage to another voltage, what your power factor is going to be. And so that's the exercise here. Yeah. Something else that we can do, just like an alternator, if you want to test it, is I'm going to have Mark read our resting voltage with our system turned off, right? So this is just going to be the resting voltage of the pack. So go ahead and read that voltage, Mark. I got this. Yeah.
There we go. Okay, fantastic. Okay, so we're going to go here, and then you go right underneath your hand, of course.
So he's reading the voltage, and we're resting at 12.9 volts, right? And so we know from our experience that's a fully charged 12 volt battery. But as they're sitting here, keep the voltage on there, we can see it going down a little bit because the system is on, it's wearing itself down, 12.83, 12.82.
So
as soon as we turn the key on, we're going to energize the DC converter. So you'll see our battery voltage go up in the same way it would if we started the vehicle and had an alternator. So I'm going to turn it on. It's going to engage the contactor, and instantly it jumped up to 13.9 volts, right? And then I'm going to turn it off, and we can see it drop back down to just battery voltage. So right there, we've done an on-off on, and we've checked our DC converter, and we can confirm that we have output. There are further exercises. We can look at our current. We can actually read the current from the DC converter and convert that to current from our main battery, and we can read current from our main battery and make sure that checks out as well. So there's some really neat exercises in here with the conversion, the DC-DC converter converting DC voltage from high voltage down to low voltage. Very relevant exercise. Yeah.
And so one of the things too on that, so it would be, so we're looking at a working system, but in actuality, students are going to get a car that doesn't work, or we're going to bug the car, so that it doesn't work. So we need to check. So we check the output of the DC-DC, but let's say it wasn't giving us our 14 volts. Then we would have to start digging and finding out why. So we need to check the input, and then we need to check the communication to the DC-DC. So these would be things, actually.
Yeah, and we even have a fuse circuit in there that students can check a fuse circuit.
So what we've got here is, and this is kind of a typical layout of how an EV would do it. So we have, this is battery voltage coming in here. We're just using this as a junction point, and then these 3 wires are going over to these 3 high voltage fuses here. So if we wanted to check our input voltage to our DC-DC, we would go here to, so this would be our high voltage negative, and then this is my, and you'll go to the voltmeter here once I get it on here. So, and then we'll go here to this here, and so you can see, so our input is, 96.8 volts. Okay, so that's what, and then if we wanted to check across the fuse, it'd be the same way. So if we had, actually we can do that here. So if I check on this side of the fuse, so it's 96.8, okay. And so one of the things on training systems or when we're teaching students, we like to bug a vehicle or bug a system so that we can simulate a breakdown, if you will. And so some of those they have like backdoor faults where you can set some computer fault or something. Everything on here, but that's not what you really see in cars. Right? You don't see backdoor keypads where you're going to type in whatever fault. Students can't relate to that. So everything on here is an actual, like it's actually how it is on the car. But what we can simply do is make sure that we're off, and then I can just pop this fuse out. Okay, so I've just taken, so this is the special high voltage fuse, take that out, and put that back down there. And so then now, if I check my system, so you wouldn't tell the student that, right? So you would do that behind the curtain. And so then if I check my system again here, so if I measure on this side of the fuse, I'm getting the 96.9. Okay. And now if I go over to this side of the fuse here, I'm getting nothing. Okay. So that should clue the student in, or as part of the learning process, that fuse, we're not passing electricity through that circuit. The other neat thing that you can do, this little, so we're looking, so kind of the goal of the Carts and Coffee was to give ideas to instructors. Is so I have the fuse, and if you wanted to know if the fuse is good, so you can hold the end of the fuse, and you can use it as a stylus on your phone. And so if the fuse was blown, then it wouldn't work to do that. So you can do a little technique if it's coming through on the camera there. So we can do that there, or swipe up or down. There we go.
That's funny, all these years.
Okay, very good. Okay, so
Well,
we
you
got my
haven't
key
had
off,
phones
and
all
then we
these
can put
years.
this back in. And then so
This is easier.
so we're getting some laughs. I'm not sure we're getting some laughs from our studio audience here, but so.
No, you think that's really cool with the phone.
Oh yeah, no, yeah, super, yeah. Well, anything to get, students are always on their phone anyway, so anything to, work with that. So, and then so with the fuse out, then if I was, and I won't go through the whole thing again, I guess, but if I was measuring the voltage, then I would not be getting charging voltage. And then of course, if the fuse was blown, the fuse, a blown fuse is the result of something. That's never going to be the cause of something. So. We would need to find out what the source, if there was a wiring problem or what caused the fuse to blow in the first place. So the other interesting thing about the DC-DC is we actually need the DC-DC turned on under 2 different circumstances, if you will. So when we're connected to the charge port, when we're connected to the charge port and we're charging the high voltage battery, we want the DC-DC to be turned on at the same time. So when we're bringing shore power in to charge the car, we want it to charge the 12-volt battery also. The other time, and then that condition would usually be with the ignition off. But the other time that we would want it to be charging is while we're driving. So if we're driving, we would have the ignition on, and then we would also want that to power up. So it's actually just using this wire here. And most systems, so this one here is just using a voltage signal, but other systems would do it over CAN bus, where it would recognize that, I'm being charged, I need to enable the DC-DC, or if the ignition is on, that it would enable it through CAN bus communication. So it can be either way you would see that. So. But that's really all there is to the DC-DC. It's actually, in a lot of ways, it's simpler than an alternator. Really, you don't have the diodes, yeah, any of that. There's no bearings to go bad. It's pretty reliable and pretty basic. So with that, let's see. So we're sitting on 1019. So do we want to take a quick break? Let's take
a quick break before Ron.
Okay, so what we're going to do is, so it is now, I see it is 10:19 Pacific time. So we're going to take just 5 minutes. I think we'll take 5 minutes. I guess you out there on the internet world, you're able to leave and use the restroom or however. We have our studio members here, so we'll give them a quick break. And then, so we'll reconvene at 10:25 Pacific time. 10:25 Pacific time, and then we'll do. I guess we'll just do we'll do a quick demo, and then at 10:30, I think Ron hopefully is. Yeah, I see Ron there. Ron, you can give us a head shake there. So at 10:30 Pacific time, so Ron's going to give us an hour of his time, and he's going to show us some cool things that he's doing there. I think he has. We're going to do an experimental something there. Yes, I'm getting the thumbs up there. Okay. So we're going to go ahead and go to break for 5 minutes. Then we'll be back, and then we'll do a quick thing, and then and then at 10:30 we'll pass it to Ron, and then after Ron is we've covered a couple things. Let's see. Do we want to? Like I was going to do the DC-DC. So let's go ahead and show a. We're going to show how to set a fault. I think we'll do that before we pass it on to Ron. So Ron, go ahead and get ready. I'll send it to you in just a second. So with EVs, they are going to have self-diagnostic capability, just like a regular gas engine, where the computer, Drew, is going to be over here. I guess that's coming through still okay. So the computer is generally part of the inverter assembly. And so it's going to have inputs and outputs, just like any gas engine is going to have. And so essentially we're taking different sensor data in. The computer has been programmed to, once I see this information, what do I do with it? And then it's going to have certain outputs that it's going to do. And then that's going to control the speed and the torque of the motor. So when there's a problem, we want to know. So in this case here, so we talked earlier that there aren't standardized codes, but there are codes. So let's go ahead and set a fault code here. So I'm just going to disconnect one of the temperature sensors. Oh, and you know what? I realized that we haven't spun the motor up. I don't know if we spun the motor up online. I don't think we did. So this does fully function. Everything on here is a regular part. And so I'm not sure, is that coming through on the speakers okay? I'm getting the thumbs up from our IT. And so, okay, so everything is running now. So I'm going to go ahead and I'm going to introduce a fault. Okay, and these would be things that you could do for your students, where you would, essentially you're going to bug the system. And that's my meter turning off there. Okay. All right, so I'm going to unplug the temperature sensor. And so I don't know if we can see that on the screen here. Is that coming up? Here we have, we're coming to a close-up of it. But we have some diagnostic codes that have come up here. And so we have and this is kind of typical for EVs as well. Ooh, that's going to be too close up maybe. Yeah. That's not. So this is showing, it's a code 19 and it's a level 2. So there will be certain codes that are more severe than others. So we would look up what the code 19 fault is, and then the level 2 is telling us whether or not it's still going to let you drive. So depending on the severity of it, it may let you know that there's a problem, but it's not going to disable it's not going to keep the person from driving it. In this case here, I am trying to work the throttle, and it is preventing me from spinning the motor. So yeah, so it is definitely not happy. That is a piece of information that it is going to want and does not have. So, all right, with that, and then so you could clear the code just with we can use the laptop to clear the code. I'm going to just plug this back in, and it is going to just clear itself once the conditions have changed and it's happy with that. And so now we're back up with the spinning. So this will be something that you can do for your students to introduce faults, and then particularly if they've been doing diagnostics with gas engines, that would be a familiar process for them, and so you're still just teaching inputs, outputs, and that type of logic and how to connect to it and extract the codes, look at a trouble tree, find out what the problem was, and work through those exercises, just similar to a gas engine. So. All right, with that, and then I see Michael standing up.
Yeah, I was just, I referenced the fault code, and it was motor over temp, right? Because it was missing the temperature sensor, and it defaulted to its highest temperature. So that's what the code was as far as cross reference. Are we going to get into Smart View at all?
We are, but we're passing on to Ron.
Yeah, all right. So we do have a different software package that comes with the inverter, and again, another free software, non-subscribed, non-cloud-based, and that lets us log into the inverter and look at historical fault data, right? So a lot of times we need a list of what happened. You might have a fault and it might just be temporary, right? And it doesn't show up on an active fault, right? So then we can go in and we can look at the logs and kind of go through. The software is really neat too, because it actually, when it has a fault code, next to it, the manufacturer's programmed in automatically common causes, right? So if we were to do the same fault code with the temperature sensor, inside the manual on the computer, it would say, check your motor temperature sensor, or your motor thermistor, right? And it would give you some guidelines for what a nice resistance is there. So it's kind of neat because it not only does the diagnostic, but then it kind of sets you on a suggested path for remedying the problem. So that's really neat.
Very good. All right. And with that, now we are going to send you to New Jersey. And so our IT is going to work the magic behind the scenes here. And Ron, I see, is queued up. And here we go. And so enjoy, Ron. And we will be back here in California with you in about an hour.
Okay. How you doing? I'm in New Jersey. This is Mr. G's workshop. We got two cameras here, one on the computer, but one on the phone. And I'll use the phone to give a tour. And we're actually going to take a ride along in a car that we converted. But I first want to address there was a question in the crowd, and you could for now just come more this way. Yeah, actually takes me like that. Okay, so, and we got Eddie behind the camera, and I'll introduce him in a second. So a lot of people ask about, let's see, what is the hardest part to teach, or for students to learn? And I would say to get them to go step by step. It's not the actual wires or the electricity or anything like that. It's to get them to go step by step and confirm each step. And I'll explain more when we get over to the vehicle that I'm going to demonstrate. But the main thing is, if you get the kids to do a continuity test, and that is just basically two wires on a meter, just making a connection. It goes beep. That means that wire from there to there is good. If that doesn't beep, then you cannot go to the next step. There is no skipping. There is no cheat code. You literally have to go step by step, and that would be the hardest lesson that I teach people. Once I learn that lesson, and once the students learn that lesson, everything's a lot easier. Okay, but it takes patience. So, Justin, I hope that answers your question. And if you have questions, just go ahead and shoot it into the group chat, or I won't be able to see if you raise your hand because we're going to take a ride along with the phone. So. But just put it in the group chat and we'll get there. Justin, did that answer your question? Anyway, he can put it in the chat if he feels like that was a good answer. Yes, that answers it. Okay, yeah, and I've been doing it for a while. 21 years auto shop teacher. Just go step by step and get the kids to confirm it with the voltmeter here. This is it right here. Actually, Here you go, Justin. This is it. This is the key to the whole thing. There's one setting on here, and that is the continuity test. You click it over to what looks like a Wi-Fi symbol, and it goes like this. It goes beep, and it should go beep. There we go. There. I don't know if you can hear that, but it's going beep, and that means it's connected. So then you can put this on wires, and you can check that. Oh, yeah. Okay. Justin knows what I'm talking about. He says he did it on a fuse. Literally, that's it. If you could just get kids to do it, but on their own, don't do it for them, you know? You know what I mean? All right. Anyway, so I'm going to show you two cars here, and then we're going to take a ride along. The first car, well, we have to switch over to the phones. So come on over here. All right. So this right here is a, actually, let me turn this up so we can hear them in case they have a question. Okay, perfect. All right, and give a thumbs down if there's something wrong. All right, so this is a, believe it or not, this is a Citroen Mahari. Okay, this came in from a customer. So I have a day job, but I also have my own workshop. So this came in from a customer. It's got an old AC Curtis controller with a DC motor down below. And this is the charger. This is the DC. This is basically the cart. The same thing that you see at EV West with Mark Weller and Michael Bream. This is it. The only thing missing from this is the motors down below, and there's batteries down below. So that's the only thing you can't see. But everything's the same. It's the same BMS. It's a Thunderstruck BMS. We got the on-off switch right here. And this car came in because several batteries were dead. And the BMS can find that. And that's the cool thing about it, is that you can diagnose the car through the computer. And I'll be honest, when they're talking about terminal interface, and they say, no problem, it's a terminal interface. You see a bunch of words on a screen or numbers. It's super boring. And I can't believe that. And they call it PuTTY, which is the terminal interface. I can't believe it because I come from like not a computer background at all. But once you get into it and you actually look at the numbers, you'll be able to see which battery is bad and which battery is good. And so that's really fun for the educator and for the students, because then they can actually see which ones are bad. Now, once we find the ones that are bad, we're actually going to replace these cells are the ones that are going to go in that car. And these are recycled, so we're actually trying to figure out which ones are good and which ones are bad. Okay, give me a mic check. I just want to know if everything's okay, and then we're going to go to the next car. Give it thumbs up or thumbs down? Let's see. Okay, thumbs up. All right.
You're good, Mr. G.
Okay, perfect. All right, so over here, this one's fun. This is the car that I converted with help from volunteers and the person behind the camera. Let me introduce you to Eddie. Eddie's a former student, and I hired him because you got to be kidding me. He's like amazing. I teach him something, and then he's better than me. So anyway, so I got Eddie involved, and we got a bunch of people to come and help out. We had students, we had adults, we had all kinds of people, and we converted this truck from gas to electric. We got to have a little fun with it because it's so good that you wouldn't know. So we did this fake drill battery. I don't know if you can see this on a camera. Can they see it? Yeah? Okay. So we did a fake drill battery, and it's almost like, imagine a drill battery, and you can actually roll it, one finger. And that reveals, ta-da, I'm going to go to the other side. What that does is it shows you that all the electronics are right here. So here's our Tesla batteries. We got three up below, 2 up top. And then we have, believe it or not, there is the Hyper 9 right down there. I don't know if you can see that. Let me just make sure there's a light on there. See the silver? Okay, can they see it in there, Eddie? Okay. And then there's an adapter plate that we actually cut from steel. Then there's a 5-speed transmission. This here is the inverter. It goes from DC 2 wires into 3 AC. This is our controller box or contactor box. Is where all the high voltages. Sorry, high voltage. And this is our charger. And this is our DC to DC. Okay. All right. So I think the best thing to do is we probably should either take questions or we could take this thing for a drive. Tell me what you think. Either questions or we're going for a drive.
Doesn't sound like we have any questions in the live audience.
What did you say?
No questions
Okay,
from the live audience.
Then we're going for a drive. All right. Okay, so we roll this thing back in, and this rolls with like one finger, you know?
I will admit there was a good chuckle when you first rolled it back.
Oh, really? Well, I got to plug my drill battery in, you know? Hey, you got the bolt? Oh,
Yeah.
Okay. Oh,
Yeah,
it's not here? Oh, did I put it here?
Mr. G, there is a question.
Okay, what is it?
Are manual transmission preferred for EV swaps?
Okay, that's a great question. And this is a manual transmission right here. Okay, that's a great question. Eddie's looking for the bolt that we had.
it's not in between this.
Oh, did I move it? Okay, I'm going to answer that question. Eddie's going to look for the bolt. The question is, okay, so it's like yes and no. So if you were Tesla, okay, and you could manufacture any type of motor you want to within reason, then no, you do not want a manual transmission. The reason for a manual transmission is because the gas engine cannot keep up with the demands. It's either too much RPM or not enough torque, right? So those are the two factors. You have torque and RPM. Torque is twisting power, and then you have RPM. So on a gas engine, they put a manual transmission. Now, if you have an electric motor that is similar in power and characteristics, torque and RPM, then you need a transmission. On a car like this, believe it or not, you don't need a transmission. The car is light enough for this motor, so the next iteration, we're actually going to ditch it. You found it? We're going to ditch it, okay? All right. Is everybody following along so far? Because then I'm going to go to the next part of this question, the answer to this question. So, Drew, give me everything's good.
You're good.
Okay. So I have an analogy to explain this better. If you're on a bicycle and you're in first gear, okay, and you're on flat ground and you start riding the bicycle, this is my foot riding a bicycle, okay? What do you run out of first? What do you don't have enough of? Is it RPM or is it torque? Right? Twisting force or is it RPM? Okay, Drew, what did they say?
I'm going to say you're going to run out of torque.
In first gear, you got plenty of torque. Think about it. The twisting force is no problem. Your leg can do in first gear. But you're going to run out of RPM. Your little legs are going like so fast. So what do? You switch it up to second gear. Now it's harder, but the ratio is that you're going slower, right? So without being there, it's kind of hard to answer this question. But basically, you need to be able to adjust your RPM and your torque so that the motor can handle the demand. Okay, so I hope that kind of answered it. And you're going to see we don't even need first gear when we drive this. Okay, Eddie, we ready for a test drive? All right. All right, we're in lovely New Jersey. It's overcast, of course, and we're gonna take this guy for a ride. Good.
And to be clear, it isn't a right-hand drive, right?
Yeah,
It's just
on the
mirrored.
wrong side.
Oh, it is
Okay, so-
right-hand drive.
Yes. So I do. It's a Japanese truck. All right. Okay, here we go. And I put it in reverse, and we're backing out. Now, if you don't know how to drive stick, that's okay, because it's easier with an electric, because you don't have to slip the clutch at all. See if anybody's there. All right, here we go. Okay, I'm going to use first gear. You're going to see we're going to run out of that pretty quickly. All right, and we're away. Well, here comes the Snap-on truck. I'm going to get out of his way. That guy's like way bigger than me. Okay, now I'm going to demonstrate a couple of things here. How's the service?
Not too bad.
All right. So I'm in first gear and I'm flooring it. I am floored, like I am flat out right now, but I limited the RPM digitally. So now I'm going to second gear. Whoa. All right, I'm flat out again because I don't want the RPM to go so high that I ruin the transmission. This transmission was not originally made for such a high-powered motor. This is about 5 times the horsepower that originally was in this vehicle. So now we're going to third gear. Here we go. Whoa. We're doing about 40 kilometers right now, 40 kilometers an hour, and that's in third gear. Now here's the cool thing. I'm gonna go to a full stop, but I'm not gonna use the brakes. Okay, I'm gonna turn the corner for a second here, so I'm not in the way of anybody. All right, now here we go. I'm off the pedal, completely off the pedal, and we're down to 0. Now, does anybody know how that happened? See what people
Regen.
say. Yes, regen, exactly. You can set the regen, and you can tune your pedal, and that's something Mark Weller and Michael Bream can explain. That's kind of like when they were talking about the fun part that EVs, you get into stuff, you can customize your vehicle to drive how you want it to drive. All right, now I'm in third gear. Okay, I'm going to show you right here. This is first, this is second, and then I'm in third, okay? And now I'm going to go straight from third. Eddie, how's the acceleration?
Pick up real quick.
Yeah. And again, here's a stop sign, and I just hit it. Now it will roll back because we're on a hill now, so I have regular brakes for that. Hill hold is an option as well. I just didn't set that up. And we're going to go back into second gear for this. And I'm going to hit it. And here we go. Okay. That's third gear. All right. And fourth gear gets a little fast for around here. Oh, it's Birdie. Come on, Birdie. All right. So it's a lot of fun to drive these things, and you can put all these digital display dashes and stuff, and you can customize, just like Michael Bream was talking about, you can customize your display, or you can just do it how it is, you know? Oh, we can turn around right here. All right.
Your service is dropping a little.
Oh, okay. All right. Okay, we're going back to the shop. Get better?
It is getting better. While you're driving, I did have a question. Are CVTs
Yeah, what's the question?
preferred for EV vehicles?
No, you want direct drive. You want manual transmissions only. There's too much loss with a CVT. Well, actually, you know what? Know who we know the answer to that question better is Michael Green or Mark Weller. I don't want to use an automatic transmission because there's too much waste in the torque converter. But a CVT, I wonder, there has to be a torque converter, right? So yeah, that's wasteful. So you don't want that. You want direct, and you can feel the torque. I don't know if you see the camera, but I'm in third gear and I'm gonna punch it. Like that's pretty good, especially for a truck like this. Now everything's opposite here, so I hit the wipers instead of the turn signal by accident. There we go. Yeah. If you do a weirdo car, you gotta remember all the weirdo stuff that goes with it. Um, did Michael Green or Weller hear the question?
Michael's here, but I think he'll address it once we're done with your part.
Okay, yeah. So anytime there's like a torque converter that's lost, and then you have to run the hydraulic pump. So you want to reduce the amount of things that you're going to waste stuff on with the electric motor because you have a lot of power as far as torque, but you want to reduce the things that are going to drain your battery. All right, here we go. Fourth gear. All right, we're doing, whoa. Now that was 70 kilometers an hour there. I don't even know what that is in miles per hour. I just know that we're on a little suburban area here. What's nice is this is a hill. You're going to see it handles this hill like no problem at all. I'm maxed out RPM right here. No issue at all. It's incredibly fast.
Yeah, compared to those little cars, usually
What's that?
they're just a little putter putt.
Oh, yeah. And I'll probably break an axle at some point. I will say I am on 80% of what the Hyper 9 can do. And the reason is because 100% slips the clutch on this vehicle, even with a brand new clutch. And so, hit the wipers again. So you definitely want to like be careful because it's like a chain. Engineering is like a chain. If you make a stronger link, all the other links are still weak. So now you have this powerful motor, but it doesn't make the transmission strong. It just makes it the same transmission. So you can end up breaking the transmission because, kids are always like, more power, and you're like, yeah, more stronger gears. And they're like, nah, that's boring. Stronger gears. Who wants that? But yeah, you'll end up breaking an axle or breaking something. That's okay. That's part of the process, All right, so here's something kind of cool. I'm going to go down a hill, but I'm not worried about flooring it because if I'm in, let's say, second gear, I can floor it, and the regen will take care of keeping it at the RPM that I programmed, which is I got 4,400. That's it. I know it does more than that, but all right. So here we go. I'm going to punch it. And there I am. I'm stuck in. It won't go faster than 20. Oh, actually, you do have to go into regen to get it to work. Oh, okay. Yeah, if you're floored in, it'll just keep freewheeling faster. So now I'm in regen on a hill, and I can stop on a hill in second gear. No feet on the pedals. We're at 0. Now, once it's finished with the regen, it does release it a little. It's kind of funny. It's like fighting itself right now. There's all these cool little settings you got to work on. All right, so here we go. We're going to go back to the shop now.
It's looking pretty nice in Jersey.
Oh yeah, this is a nice spot. I found a good spot for the workshop. I wish I could buy the place. It's like amazing. Yeah, it's a good spot. And we should probably show them the neighbors. We have something special at the neighbors. Something you've never seen before, ever. You heard of 3D printing? Of course, right?
Of course.
Well, these guys have a 3D printer the size of a truck. So they're 3D printing like furniture.
That's cool.
Yeah, we won't get too distracted, but I'll take it. I'll take a peek next door just to pique interest and get people excited about engineering and all kinds of stuff. I mean, the main thing is that if there's educators on this phone call, let me tell you, you guys are the future. You're really helping out these kids because you imagine not learning any of this and you're just academically book smart, and then you're gonna do like what? You're gonna work on the SAT scores? I mean, they got AI now. So you need to learn how things actually get made, and you need to be on the cutting edge. Otherwise, you're just going to read about it in a book, but you need to do it with your hands, not just the books. So I think anybody on this call right now is making a huge step right now. So thanks for being here. I really appreciate it. All right, we're going to pull.
I ditto Mr. G's comment there. Thank you everyone for joining us.
Yeah, it's huge. It means something because every teacher represents like 100 kids a year, so that's like that's a lot of people, and maybe they're gonna reach everybody, but they'll at least have an influence on 10. So like that's 10 more kids that got to get started earlier, in their career. Okay, so that's that. Let's go take a look at the machine. Okay.
And Mr. G,
Yeah.
just so you know, I've talked to the team here, and if you do your quick tour, then we'll probably come back on live here.
Okay, cool. All right. So I'm gonna show you I'll show you the robot real quick. It's insane. You just have to see it. And then we can lift up the truck later, and if you want to see underneath the truck, so they can see how a motor, transmission, and all that gets hooked in underneath the vehicle. It's pretty easy to lift this, so we can lift it up while you guys take your turn. Okay.
Sounds fantastic.
Let's watch you step. Hey, the robot. Okay? Yeah, take a look. All right. Watch you step. Can everybody see that? It's 3D printing.
Massive.
It's like automotive level like robotic arm. Yeah. Okay, we're gonna leave. You guys are busy.
What was he printing?
What's he printing? I think it's a lot of decorative stuff, so I think it's like a wall decoration or a piece of furniture.
10-4.
You can zoom in on that.
Oh, that's cool.
Maybe it goes in a window or something. And if you come over here for a second, this used to be a Packard dealer, Studebaker and Packards. And then it was a transmission shop. And so this is the building here, and I just rent this over here. So yeah.
Mr. G, I did have one more question.
Yeah.
So are you digitally programming each gear? I'm sorry. Are you digitally programming each gear to be able to limit the power output?
No, I just limit the motor controller to 4,400 RPM and 80% torque, and then I can shift gears manually. So the trick is don't tell the car what you're doing. Like the car has no idea. We never told the car what's going on. We just talked to the EV parts. That's just like a silly joke about it. But basically, the car has no idea what's going on. So the transmission's just acting normal. Does that answer the question?
I think so.
Yeah.
And Mr. G, I think we're ready to go ahead and swap back to the other crew.
All right, perfect. Okay, cool. And then we'll get this car lifted up so that it'll be on the lift, and then we could peek underneath if that's something you guys want to do later.
Yes, we do.
All right, so we're going to do a couple other things here. So I'm going to go. Do I want to do this one now? Yeah. So we're going to do a little work with picoscope. So picoscope is so it's a lab scope. So one of the hardest things teaching electricity or electric vehicles is you're teaching something to students that they can't see, and so they definitely do need to have a good understanding of electricity. And ideally, if you have an EV class or a hybrid class, you want to have the students take a regular electrical class first. Would be ideal. We kind of learned here so there is a difference between an electrical 101 and an EV 101. And while there is plenty of overlap, of course, we've found that it's kind of better to just have two separate classes, just get them set up on the foundational good electrical foundation, and then go ahead and introduce the electric vehicle portion, and it goes smoother. And you could do those as possibly a co-requisite, but ideally it would be a prerequisite to have an electrical 101 and then go to an EV 101. So, but yeah, so we like using the picoscope because now you can, and there's plenty of other scopes that you can use. It doesn't have to be, but this is one we like, and it does seem to be pretty popular with schools. They're not that expensive, really. No subscriptions required for this either, which makes it nice. You just buy it and you have it. And then actually I just updated, unfortunately, we updated this last night. So yeah, so we have some pre-programmed stuff here. So I'm just going to show you, so we're going to look at CAN bus, and then I don't know if Michael will do some of the, so CAN bus is the computer language that most cars are talking in, or one of several, but kind of the main one. And so there's kind of two sides to it. So you have the physical part of it where you have the actual wires, and then you have the digital part, or the programming part where you're going to, what are all the addresses and what do they mean. So we're just going to take a look at the physical part of it right now. And so this is becoming more as there are more and more compute. And actually what I'm going to show you, this isn't really anything specific to EVs. This is just kind of just general CAN stuff. But we can totally do it with the trainer here very easily. So I'm just going to go to communications right here. And then we're going to go to CAN bus. I don't know if that's coming through on the screen, but I'm just using CAN bus. So there are some different ones. So K-line, Lin, so these are some older ones. FlexRay, that's another big one that's coming. But we'll just go with CAN for right now. And then we're going to look at and then this one can do, so we're going to look at the physical layer. So we're just going to look at the scope pattern of it. But it can do serial decoding. So if you're into programming, and you'll have some students that will be like all into this. So like for, if you have IT classes or students that are into this. So we'll go there, and we're going to go to load settings. And so so it makes it nice because I'm just using the guided test, and then it just loads it up there. So this is giving us an example of what it should look like. Right now we're stopped. I'm going to go ahead and change that to running. And then we'll need to turn on the system. So we're going to be on. And so now we're looking at the active messages that are coming across here. And so really, to us, the value in this is whenever the network goes down, and you have a couple computers that aren't talking to each other, we want to know if you're getting good signal. We don't necessarily need to interpret what the messages are. We just want to know, are the messages being sent? And so that's kind of the beauty of this here. And so that's kind of how that goes. And so that gives students, a visual of what's going on. And then if we can come over here with the camera guy, So we have a little bit going on here with stuff, but so all we have is, so we just make this little breakout cord. And so this would just normally be connected here, and so we just put this little breakout adapter in. Whoops, and then I probably just lost my signal. And actually, so let's take a look at this. This worked out good. So I just had one of my signals. It just came unplugged here, but I just dropped out. And so we were talking about things that we can do to bug a vehicle for a student. So we do want to be able to see what happens when one signal goes away. So there's my, that must be CAN high. And then this would be CAN low when it drops out. And then I think, and I haven't done it on this one here, but if we short the two together, let's see what happens there. Okay, so we're just back at 2.5, but we're not sending messages. So then I think we can, yeah, so we'll leave it at that. I wasn't prepared. I could have done a couple more with that. I just realized kind of on the fly here. But anyways, that was the main thing, is just to get the messages up there. But you can tell, so basically it's just two wires, usually twisted pair. And so depending on if it goes high or low, and which wire, then you can determine where the fault is, or which wire the fault is on, or what's occurring. So that makes it kind of nice.
Yeah. So, CAN communication was designed. It was originally invented with the sole purpose of communications within a car by the Robert Bosch company. They found out a long time ago that a lot of these low voltage data communication standards, such as serial, are really not immune to the RF interference from the high voltage systems. So, and this was done before EVs were a thing. What they were actually seeing interference from was the high voltage ignition systems in cars, which run up to 50,000 volts. Those systems can interfere with the communication standard, and because of that, we have CAN bus now. And CAN is a much more robust standard that allows us to have these communication devices within the vehicle, and they're immune to this RF interference. So it's not anything new. It's just basically a bigger, better hammer. We've always been communicating, but now we have a standard that is so much better, and it can handle more information and more bandwidth on the bus. I did want to mention, the question came up to Ron about CVT transmissions, and he did a pretty good job of discussing it, but I just wanted to point out, when you have a combustion engine and you look at a dyno chart and you look at power, it generally looks like this. And you have this area of peak power right here that you want to stay in. And so as your RPM increases and you go out of this peak area, you shift to come back and stay in it. So this shifting is required to keep peak power. So the CVT was really designed for a combustion engine to stay in this zone. When you look at a dyno chart of an average electric car, the power kind of comes up and then planes off like that, because the actual torque level is more like a mesa. It's flat like that. So the electric car can kind of operate with good efficiency at a much wider window of RPM. And so that's the main reason why a CVT isn't going to be as effective in an EV, because the EV is more effective at a broader RPM range, where it stays in this peak power range pretty much all the way through, and the combustion engine is a lot more truncated. Yeah?
And there's just too much loss of power in automatic transmission, correct?
Yeah, and again, we're doing the same thing. We're kind of, the whole point of an automatic transmission, especially nowadays, it's crazy, because just in the last decade, we've gone from like the standard trans having maybe 4 in an overdrive to now 10, right? And you hear them. You go and drive like a brand new F-150, it's just boop, 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 boop. It just stays in that zone. Now, there's a couple reasons for that. One of them is CAFE standards, right? They have these fuel standards that they have to abide by, right? And the transmission, if you keep it in this zone, is going to stay more efficient for most of that time. And so that's really why they're doing that. And the neat thing is that the electric vehicle, because of its continuous torque, doesn't need that. And specifically to automatic transmissions, when you look at the actual foot-pounds of output, just torque on an electric motor, it looks like this. So It's like a Mesa, but it's slightly going down, and your highest torque is actually right there, starting torque at 0 RPM. And we all know if we put an automatic transmission in here, we'd have a torque converter, and let's just call this like 1500 RPM. It's going to ignore everything below this. It will just slip, right? And so we're taking our most powerful RPM range and just throwing it away. And so that's why you can't really use an automatic transmission. So there's some workarounds, and we've done some things like, the electric motor doesn't idle, so it goes down to 0 RPM. Once it hits 0 RPM, the internal transmission pump's not running anymore, and you lose internal pressure, so you can't switch the valve bodies or any of those mechanisms. We, kind of went to the edge of the earth to see, hey, can we make this work? And we used an external hydraulic pump. Pumped that up to 200 PSI and pushed it into the transmission, and we were able to use an automatic transmission all the way down to 0 RPM. And even though we got it to work, it was pretty awful. Yeah. Not very efficient. So, and it's so neat, like Ron was talking about manual transmissions, and the neat thing to understand about a manual transmission, if you just put it into gear and then don't touch it, and don't touch the clutch, and don't slip it, that's a direct drive fixed ratio reduction. And so if you just take a regular transmission and just put it in second or third gear, that's essentially the exact same drivetrain that you're seeing in a Tesla or a Leaf, right? Any of those vehicles. Yeah, single gear reduction. Yeah, generally around 8-to-1 to 10-to-1, depending on the RPM and the tire size. Yeah. So the question was, if you could essentially tailor make a CVT for an EV. And you could kind of really focus in on that prime efficiency RPM, because all motors, right, whether they're gas or electric, are going to have an RPM that represents peak efficiency. For an EV, it's around the knee. It's right around this RPM here where the torque knee drops off. Just before that is the most efficient point. So you could pinpoint something like that, but the actual parasitical loss in the transmission itself is greater than you would get with a normal ring gear, like gear-to-gear reduction, right? And you see it, like you actually see it, like if you take a normal differential out of like a rear axle and you go and you spin that differential, right? It takes a lot of force just to spin the input shaft, right? You can do the same thing with a Tesla motor, that instead of having a beveled ring and pinion for the 90-degree going out to the wheels and the axle, what they do then is they just turn the whole motor transverse, right? Just like a four-cylinder front-wheel drive car. They did that to get the efficiency more than anything, right? Because a front-wheel drive car doesn't have that 90-degree differential in it. So now when you do the reduction ring gear to ring gear, you can actually go up to one of these Tesla units and grab the shaft outputs and spin them, and the motor will actually coast for a little bit. That's how much more efficient it is. Like there's not a differential in the world. You can walk up, spin the shaft and let go and have it spin. It just won't do it. There are so many losses in that. In fact, if you start getting into the physics of motion transfer, there's nothing more inefficient than taking motion one direction and changing it exactly 90 degrees. And that's what a differential does. So literally, the differential, by definition, is the most lossy transfer of power that we can come up with, right? And we've really been limited by the architecture of combustion engines, right? The heat that comes off a combustion engine is such a limiting factor that we have to put the engine way out in front and then cut a hole in the front of the car and put a grill over it and let air fly through there. And it rattles so much and it needs so much of its own space, it can't actually be mounted on the driveline, so now we got to put a tube down the center of the car. It doesn't fit well, so now we got to build a hump into the car. See where this is all going, right? And now, what's really, and this has driven the shape of vehicles, right? Like the way the cooling system is, the exhaust, the drivetrain, everything. This has literally shaped the aesthetic design of a modern sedan, right? And now we've taken that sedan, taken the shape, and we've rearranged the components, right? An electric sedan doesn't necessarily have an engine under the hood. Generally, the hood is reserved for cargo compartments, like a frunk, right? So we kind of have that transition going on where we have the leftover kind of architecture of the car, but we're changing where the bits go inside the car. And that's really exciting, especially when you're involved in conversions, because you're taking cars that were designed by engineers for one purpose, and we're kind of changing it. And what a lot of people initially do when they go into this is they say, well, my combustion engine was up front, so that's where my electric motor goes. But the actual reality is that's the worst spot for it, because your electric motor is very lightweight compared to a combustion motor. And what's very heavy in an electric system is the battery. Right, so you generally want to put the battery up front where the motor went, and the motor is so lightweight, you can generally put it on the axle where the differential previously was and add just a nominal amount of weight. And the car itself will have very close to the weight distribution that it came out of the factory with, but the functionality and the location of those components are drastically different. And so that's really fun. That's fun for us. You know, you go up to an old V8 car and you pop the hood and you're like, it's a battery. There's not even, and a lot of people without this knowledge and the design knowledge would just want to put the motor up there. But if we just take, say for example, like a mid-60s Corvette, and we put a little Tesla motor up front, right, where it normally had a 327 V8 and a 350 trans that combine weigh 700 pounds, 600 to 700 pounds, and we're putting in a couple 100-pound motor, we all know that car is going to really suffer from understeer, right? And we're going to compound that problem now if we put a 600-pound battery pack in the back, right? But what we know is we can put a 600-pound battery pack in the front, and that's just going to replace the engine weight, and then we can remove the rear differential and put a motor back there, and now we have a car that is really, really close to its factory weight and its factory weight balance between the front and the rear, the displacement and the bias. So the question was, what are the thoughts on electrifying the rear drivetrain and having combustion on the front drivetrain? And I apologize, I gave a snarky answer. I said you're halfway there. If you think about where this is going, and if you think about the electron as a form of fuel, right? We can all look at gas, and we know gas weighs approximately 7 pounds for every gallon. We can't change that. It's been that way since the first automobile, since Daimler-Benz rolled the first one off in 1888. It has been that way. We can't change it. What's interesting about the electron, our new form of fuel, there's almost no weight associated with it, right? I think it's 9 micrograms is the amount of weight a car will take on being fully discharged and fully charged, right? It literally is, you can't even, we don't even have the instrumentation to measure the difference that it weighs. So really what we're talking about is the vessel to hold the energy, right? So this would be like saying, I've got this incredible race car, I filled my gas tank up with gas, but my gas tank weighs 1,000 pounds. If I can just improve my gas tank and get it down to 500 pounds, I'm going to improve my overall car, right? I can either double my fuel or half my weight. And that's exactly where we are with batteries right now. We're focusing on the vessel, right? The actual battery just holds the electron. It's not the electron itself. So this is the thing that gives me so much promise. And I really hope that some of the teachers out there are able to, carry this forward to their students and teach this. But there is so much to gain at this point. We've got, when you look at it, it's almost like there's not a limit to how much weight we can pull out of the structure of a battery, right? We're just looking for a storage facility for our electrons, right? And that's why we're seeing consistently, I've been in this 20 years now, and consistently we're seeing about 10% energy density increase every year, right? So it's not going to be a big breakthrough, but you might kind of get out of the market and then come back in 7 years later and realize batteries are about twice as dense as they were about 7 to 10 years ago. And we're going to keep seeing that. And we're going to get to a point now where, if you look at the first electric cars, they were like 70 miles range, right? The Leaf. And then the first version of Tesla came out and they were hitting 200 and people were just blown away by that. And then 300 and then 400 and then 500. So we've already made that jump from 250 miles range to 500, and we made the jump from 125 to 250. So we've already doubled twice in the short time period. If we can double this again and get to 1,000 miles of range per charge, you now have an algorithm for the average American to only charge once a month. And what that does is that opens up electric vehicles to all the consumers that live in shared housing, right? If you're in an apartment complex or a condo, it's very difficult to charge your car. You might not have assigned parking, et cetera, right? But now, because of this constant progress, we have an algorithm that works where you can go out to dinner one night a month, go eat your meal, come back out to your car's got 1,000 miles of range on it, and you don't even need to think about recharging it until the following month. And I think we're going to see more and more of this. I'm a big motorsports guy, and I cannot wait till we see the day that we can race a Baja 1000 without a single pit stop. It's capable. On paper, this is a possibility, right? This isn't crazy talk. This is something that if you look at the measured progress of where we come from, and you extrapolate that progress out, this is something that's coming. These types of ranges, measured in the thousands of miles. It used to be measured in dozens, and then it was measured in hundreds, and it's soon going to be measured in thousands. And it's really exciting. And a lot of this is going to be driven by other industries. Aviation and marine are two really huge ones that have different uses for that propulsive power. They need more of a continuous power than vehicles, which is a little bit more non-continuous.
So we're going to go ahead and take a look at some drive-away protection. And so what that means is, so when you're filling your car with gas, okay, so there are some safety protections there that, so you have the gas nozzle in, and you're busy, maybe you go in to get a coffee or whatever, and so you inadvertently drive away with the gas nozzle still in the car, right? So, but there's a breakaway so because they expect that that's going to happen, and so that that's all safe. So we have the same thing with an electric car. Okay, so we're going to be connected to, and actually, let's see, I don't know. Yeah, I guess it'll do it from the back side there. Let me get rid of this here so that doesn't confuse.
So this is a required safety standard under FMVSS 305. That's above my pay grade, but it's an agency that regulates this stuff, and it's mandatory on all road legal vehicles that there is a propulsive inhibitor. That's the law, right? And so what's interesting about this is FMVSS 305 really only governs the manufacturers, right? So the manufacturers are under this law, but it doesn't look like any of the small manufacturers are or DIY conversions. But to stay clear of the law, this is a feature that needs to be put into the vehicles, if that makes sense, right? So in other words, it would be like a seatbelt law, where the seatbelt law requires all new cars to be sold with a seatbelt, but there's a fine line there that doesn't really say you can build a car without a seatbelt, but it doesn't necessarily say that you can't. But I think we can all agree all vehicles need seatbelts. And it's the same thing with these drive-away protection systems.
All right, very good. So so we're going to have, so there's going to be a charge port on the vehicle, on all of our vehicles. And just to, for in America, basically it's come down to two different styles. So you'll have the J1772, or you will have the Tesla port, which they have the same number of pins. And this is actually what I'm using for this demo is an adapter that allows you to use a J1772 with a Tesla, if you're charging a Tesla car. But it's going to work for this little demo for what I'm doing. So what we need to do for drive-away is that whenever I'm connected to the charge station, I want to not be able to drive the car. So let's, I don't know, well, yeah, I guess we'll do it that way there. Okay, so if I have the car turned on, so can we get the camera angle? So I guess we got both of them up there. Okay. not running? You're off. Because I turned it off. It was on and then I turned it off. Okay, all right. So I'm trying to do things behind me here. So okay. So we're running now, and so what we want then is that whenever we're plugged in, then okay, we should not be able to run. Okay, and so what we have is over here. Yeah. So that we just have there's just a driveway relay up here, and so whenever it's connected, then the computer is turning on this relay. To let the inverter know, hey, I'm connected to a charge station, and then it won't let it drive. So then whenever I disconnect, and then I'm able to drive again. So that's basically the gist of driveway. And there are, so you do have some communication that's going to be, am I showing up on the camera there? So there you have pilot and proximity. And this is another good one to, I like to pull this up on the Picoscope. I don't have it set up to do that right this second here, but you can totally scope these and students can see what's going on in the communication handshake. And the other neat thing is whenever we're doing the programming using the PuTTY program, we were up on there earlier, you can go in and you can set the charging amperage for how fast or slow you want the charger to be able to charge. Now, part of that will be based on the capabilities of the charger itself, but it is neat to, like, I guess there's a certain level whenever you're designing and building an electric vehicle, as opposed to just whenever you're learning, how a manufacturer has already designed it. So whenever you're the one setting the parameters, there's just a level of learning there where you really understand it. And then at that point, once you have that deep level of understanding, it really is no longer about what brand of vehicle it is. Throw me any vehicle, and you understand what goes into how it's made, and it just makes fixing it a whole lot easier, really. It's like I've sat in on, I don't even know how many Toyota Prius classes. And but until you start designing, and whenever I started working with doing conversions, then it's just a deeper level of understanding. So some cool things that we can be teaching students, and some of your students are going to be future engineers, and so they'll be designing the cars that we'll be driving one day. So we are going to, through the magic of technology, we are about to transition you from California back to New Jersey. So, Ron, give me the nods, the thumbs up there.
So underneath here, this is my setup. Now, as Michael said, the ideal setup would be that I do not turn 90 degrees here. That's true, but this is a motor swap and not a drivetrain swap. So in other words, this is kind of a minimal setup. This is not ideal setup. But what's nice is you could see what's going on. So there used to be a gas engine right here, and it went up to about there. And then there was a pass through, like a little tunnel right there for the radiator. So that's like where the radiator goes through there. And what's kind of cool about these mini trucks is they're built kind of like a sports car. They have a mid engine. It's right underneath your butt, basically. It's where the door is. And then here's the 5-speed. And it's got a cable driven shifter. And so then here's your transfer case. And that's your four-wheel drive back to the front. And then this is the rear drive shaft, and there's your rear axle. So it's a pretty simple setup. And there's a cross beam that has these bolts right here, and it comes right out. So I chose this setup because it's pretty easy to work on with students. You can drop the whole transmission with just a few bolts. And the transmission hangs onto the motor, which has an adapter plate. Adapter plate looks a little rusty now, but that's because it's made out of steel. It's a prototype. But we designed it and built it right here. Just took some measurements and made some cross members. And we made a coupler as well. And this is something that your students can do after training themselves up on the cart. This is essentially the cart. No problem. So anyway, I just thought I'd show you that, how simple that is. And then everything else you just leave alone. Just leave it as a regular vehicle. And don't get me wrong, you got to have a vehicle that has good bones and foundation. We got some rust problems here, and we're going to fix all that. We started fixing it here. We patched a lot of spaces. But just to stay on track here, I just want to show you what's possible. And this is 5 times the horsepower that it normally had. The original gas engine is sitting here in the corner, just collecting dust. So anyway, cool. I just thought I'd show you that. Give you like the overview. Okay, no problem. Back to you guys in the studio.
All right, and just like that, we're back in California. So we think we're just going to, any questions? At this point, we're just going to go to questions, and then we will work on wrapping up here. So.
Yeah, questions or comments. We want to thank you all for attending. This is the first time doing this, so we apologize if we came off a little less than professional, but we're trying our best over here. And we really, you know, we're not presenters by nature, obviously. You know, our primary job is Mark's an instructor and I'm an engineer. And we worked together through his experience in the classroom and our experience of a couple decades of building, you know, highly reliable, safe, and serviceable EVs, and then using that relationship together to see what the classroom needs are and to see what the system needs are and come up with what we feel complements them both. And again, I think Mark and I really enjoy this. It's been a joy for me to start doing the teachings. We're doing these classes now the past couple of years, and I feel like sometimes I come out of the class learning more than the students did, and that's a result of comments and feedback, right? So Mark and I really want to make ourselves open. If you don't have a question now and something comes up in the future, please send it to us. You can go to the ev-trainer.com website and, you know, use our contact information to reach out to us directly and ask those types of questions. You know, we're here for you. We take suggestions too. If there's any teachers out there that have a need or maybe see a component or a piece of curriculum that we're missing or maybe should be addressed, we would absolutely love to hear from you and address that in the training cart. So, but just very much thank you all for joining us, and yeah, we're going to open up for some general questions and conversation. So the audience member was asking a question directly to Mr. G, Ron Grossinger, about his K-truck that he drove in.
What was the biggest takeaway? Okay. Well, I would say, you know, I learned a lot about this stuff when I was in California, where the weather's nice. So I think that the version 2, I'm going to try and do much more waterproof. And then that would be one thing. And then the second thing is I think direct drive with this weight vehicle, I mean, I think it's only 1,600 pounds. That Hyper 9, you don't need a transmission for this. So that would be the second thing I learned.
But you wanted to preserve your all-wheel drive too, and that was maybe one of the reasons for going that way, or what?
Yeah, but you could still, I would maybe spend the time to come up with a clutchless system and keep the transfer case. So that is a custom part that was not available.
Because your clutch is like your weakest point here, right? That's what can't take the horsepower.
So far, but I'm sure if I somehow got a better clutch and I was able to put it to 100%, I would probably break something else.
Right, it's preventing you from snapping your transmission into pieces, probably. But
yeah, probably. I had a transmission guy tell me that it's probably already happening. So.
Well, good thing you got some spares laying around, other rusty hulks of K-trucks and around there. So.
Oh yeah, this is like, I don't know why, but there's it just happens to be that people are so excited about this K-truck. So it just happens to be that the landlord that I rent from here imports them. So yeah, there's like a yard filled with K-trucks. and I got one of the cheapest ones because it had a lot of rust on the frame, but I didn't mind doing the rust repair. So I would say, yeah, oh, and be careful with the rust repair, or if you're buying a K truck, what they do is they take duct tape and they put it on top of a hole, and then they Bondo the duct tape and spray it black to match the frame. Oh yeah, oh yeah.
So go poke it with a screwdriver and see what's really
Poke it with
metal.
yeah. You need to poke
I
the
think
frame to find out.
I think it's worth pointing out at this point that Ron's talking about a project truck that they have in his shop that students are coming and helping him with. But what's not lost on me is the variety of exercises and tasks that they can do. You were talking about maybe going all-wheel drive or not, or running through the factory drivetrain. So there's all these arrangements that you can do in that car, and you pointed out very accurately, we weren't doing a drivetrain swap, we were simply doing a motor swap. So that's kind of neat because it kind of highlights the depth at which you can become involved, right? So he did, with his students, that kind of first level, right, which is just a motor swap. But he's already talking about now doing a drivetrain swap. Did you notice that? He was talking about direct drive. So he didn't even intentionally do that, but he was just kind of talking through the process. And this is the type of stuff that we see from instructors in this area, where they build that foundational knowledge and then just kind of want to keep building on top of that foundation and going to the next level. So that's great. There's a lot to unpack with controlling an electric motor and a battery pack, and he's already gotten past that. Now he's getting into the minutia detail of the actual drivetrain and fixed gear ratio reduction, tire size calculations, starting to look at dyno charts and putting the motor at the most efficient RPM for the vehicle that he has and its use case. So this is really neat stuff. Imagine getting into a combustion project and then immediately just diving into all of that stuff. It's really neat to have such a finite system, and one that's very binary. It works or it doesn't. With automobiles, they can be with the combustion engines, they can be a little bit more nuanced, right? If you have your timing just a little bit out, you might not be running peak power, right? If your fuel ratio is slightly lean, right, you could be overheating the engine and making the engine work a lot harder than it should work. And so a lot of those things where, you know, I kind of giggle if somebody puts a gas car on a dyno, flip a quarter, you almost don't know what you're going to get. And from one day to the next, you might get different horsepower levels. You might even get different horsepower just based on the temperature, right? The ambient temperature and how much water is in the air. So with an electric motor, that doesn't exist. If you have a certain amount of voltage and a certain amount of amperage, you are going to get that much wattage, that much horsepower. We did, I think the first time we went out to Bonneville to do land speed racing, we did like 4 or 5 runs on the 5-mile course, and like all of our runs were within like a mile an hour or 2 of each other, up in the 240, 230 mile an hour range. And it's insane to think about that, because just a 2 mile an hour breeze that just shifted could change that speed. So to consistently do the same thing over and over and over and over and hit those same exact levels speaks to the consistency of an electric drivetrain. So if we were going to go out and put this on a dyno today, a year from now, 5 years from now, we'll hit that same number every time. In a combustion engine, over time, they hold less compression in the rings. There's things that wear down, and it's a little bit more foggy as far as how much power you're going to get out of it. Or stating, like measuring the power and then saying this is the maximum power. That's a little bit tougher with a combustion engine, whereas the electric, you can do all the math and be like, this is the exact amount of power we should be seeing, and then you can proof that out by going into a dyno and seeing what kind of power you're getting back out of it. And we've done that in real life with our race cars here, where we've put them on dynos. We got a question from the audience.
Yes, so would that power be the same, let's say 5 years from now, with the deteriorating of the battery, or?
Yeah, because capacity isn't power, right? Capacity, so there's two things. There's the energy, right, that you're going to have, and then the power. So the energy is my range, right? My total amount of energy in my car, say, will let me go 300 miles. But the power might let me go 150 miles an hour, right? So if you take a car with a 10-year-old degraded battery, on average, the industry right now is seeing 1% degradation per year. That's an industry average, right? It's actually 9, just less than 1%. So if you take a 10-year-old car, it's very safe to assume that it's going to have 90% of its original energy. But when you charge that car, the individual battery cells themselves will all charge up to 4.2 volts, right? So the voltage now is limited by the battery, and the current is limited by the motor inverter, and that's going to have a maximum current. So what we have here is we have a battery that can physically output up to about 12 or 1300 amps, but it runs into an inverter, and the inverter can only max 750 amps. So it will never overburden the battery, right? This is just like our wall. I got 15 amps of current coming out of my wall. I plug in my vacuum cleaner and it's only going to pull 8 amps, right? It's not going to pull all the 15 amps that are available to it. It's only going to pull what's equal to its load. And that's what electric motors do really good at. When they're sitting there idling, and the whole time we've done this demonstration for 3 hours, this has been sitting here idling. We wouldn't do that with a car, right? We would turn the engine off, it'd be creating heat and noise and all that. And during the 3 hours that this cart's been on, we've probably used like almost not even measurable amount of energy, right? So that's what's neat about the car, and specifically the electric drivetrains, right? In combustion, you have this kind of dichotomy where you have some of the fastest engines in the world, but they're the least efficient, right? They're going to get 2-3 miles to the gallon. Race engines, 10 miles to the gallon, just awful. But in electric, one of the most fascinating things, especially for like a gearhead like me who loves racing, loves speed, loves horsepower, is when you make an electric motor more efficient, you make it more powerful. And when you make an electric motor more powerful, you make it more efficient. It's crazy to see this relationship. A real world example of this is the single most efficient car in the world that you can just go out and buy is a Tesla Model S Plaid.
That's right. It is.
It's also the fastest car that you can go out and buy. I'm ignoring the sports cars that look like rocket ships, but my mom drives a Tesla Model S, literally driving one of the fastest cars in the entire world, and then the engineer in me is like, my mom's driving one of the most efficient cars in the entire world. That's never happened before, right? So it's really exciting as a car guy, because I'm looking across the desk at all my fuel efficiency nerds, and we're on the same page now, right? In combustion, they fight against each other. This guy over here wants 50 miles to the gallon, and I want 500 horsepower. We are at odds with each other. But with the electric drivetrain, I want a megawatt motor, and I'm like, yeah, and he wants a motor that's going to do like a mile on 200 watt hours. But our interests are aligned. So that's one of the fascinating things when it comes to electric motors.
All right, just so you know, the mics are dead, so everybody can hear in the room right now.
Okay.
So any more commentary is great. If we're ready to shut it off, whatever we got from here, it's up to you
Okay.
guys.
Any more questions from online? Okay. Audience question?
One more audience question from Tom.
Tom?
Yeah.
Do you want to be on TV?
No.
No, it's
No.
good. Okay, all right.
So I'm in the room with 3 beautiful carts. I know there's a lot of expense involved in putting these together. Some school districts are wealthier than others. What does it cost for my school district to get into one of these? And can we get do you have different models of carts?
Well, what does it cost your school district to not get involved in this, right? So we talk about the carts, and especially school districts, especially when you get to the collegiate level, right? Now students have a choice of where they could go. And are they going to go to a district that's looking forward, right? Looking at the world as their stage instead of just their backyard, right? Because right now we're at a time where EVs are taking off at an exponential rate, like crazier than we've ever seen it. We don't visually see it on a daily basis because we have some headwinds in the United States, right? But in the world, these projects are just taking off. If you look at European numbers and numbers in Asia, they're breaking sales records pretty much every single month, right? And for a school, its sole purpose is to prepare, the youth for tomorrow. it seems more costly for a school to make a conscious decision that they're going to stay on a fuel standard that by and large, the entire world is abandoned, right? Now, Americans are very nostalgic, right? We love our cowboy hats and boots and all that stuff and old stories. So we're going to be on gas for a while, but it's an artificial nostalgia that's keeping us on it, right? We all know there's a better fuel. That's a done subject, right? At this point, it's just nostalgia keeping us on gas. But you can't tell your kid you're going to have a whole career based on nostalgia, right? It needs to be based on what the world needs: safe, reliable, sustainable solutions. And that's what this is, right? And, you know, we're not here to sell cars, so I don't want, you know, the cost is online. People can go online, they can call us, they can reach out. We work with school districts, we've given discounts for, you know, and I don't want to get into that. None of this purpose today was sales, right? This is all about just instruction and knowledge, knowing that these components exist as an aid to help people prepare their students, right? They're going to be judged afterwards. And if they're putting through whole classrooms of people going out trying to find jobs in an industry that's shrinking, that's irresponsible, right? So right now, the responsible thing would be to prepare students for these technologies where the opportunities are growing daily. I mean, you look at any of the companies right now, there's across the board, big corporations in America are cutting back and they're pulling back. But if you look at the Lucids and the Rivians and the Teslas and all these in the world, they're all expanding right now and they're all hiring. And as educators, our job is to prepare people for those markets. And again, it would be irresponsible to teach based on nostalgia instead of actual numbers of what's going on in the real world. Yeah, it's a great question.
Are there different models though? I don't know if you got that.
There are, great question, yeah. So the most important thing is that these are systems that resemble the systems that we sell. And I'm sorry, we didn't have a microphone. The question was, are there different models of carts? And so the answer is yes, there's a couple different models. We have the low voltage ones that start at 100 and 120 volts, and of course we go all the way up to the Tesla carts. And we can customize parts based on requirements as well. If there's a certain requirement or a certain voltage or horsepower need, we had one of the carts, we had a school wanted to do a small motor, just neighborhood electric car stuff, golf cart stuff, and we manufactured a cart specifically with that system on it and sent it out so they could train on it.
And I'm assuming if you work with school districts before, you accept POs?
We do. It gets a little, that's not my department. But yes, we do, but it largely depends on the school. Right, yeah. Yeah. So.
All right, I think that covers everything. You can go ahead and cut it off.
Yes, you do it.
Okay, so there's no last minute questions. Then I think we'll go ahead and wrap it up. And I just want to, just a really, really big thanks to our staff that's helped out, and Drew and Margarita.
A ton of behind the scenes to make this all happen.
We appreciate, EVLC. If you're interested in any EV education or learning or extra classes, check out ev-lc.org. They've put on the facility here and the ability for Mark and I to do classes and teach. We very much appreciate them. And Mr. Mark Well, I appreciate him very much too. I'm not sure if I missed anything.
I appreciate you too.
So the website for the school is ev-lc.org, and that's EV for EV Learning Center, ev-lc.org. Yeah. And again, I think Mark and I really enjoy this stuff, so you can always reach out to us at EV West and get a hold of us Monday through Thursday. Or Monday through Wednesday for Mark. He still spends a lot of time in the classroom. He's a teacher.
For that too, yeah. So I run the education department with EV West, and I'm all around the country doing different trade shows. When we deliver these cards to school, so it's entirely possible that I can meet up with you in some part around the country. I don't know if they're still online. There's somebody from Pennsylvania. I'll actually be heading, so that's my stomping grounds there, so I'll be heading out there at some point. Anyway, Yeah, so you have the opportunity to meet me live, see the cart live, somewhere around the world. We'll be in Sacramento.
Yeah.
We'll be there's a training in Sacramento in June through the NACAT. So I'll be there. I'll be in New Orleans at the end of the year.
Yeah, come say hi to Mark on the road. If you're an educator and you're in these events, come say hi.
All right, with that,
By the way, when's the next NACAT?
we'll talk online.
Okay.
Yeah, so.
Okay,
All
with
right,
that, thank
call
you.
a wrap. Thank you.
Ron, thank you so much, Ron. Appreciate you
Yes,
on the
Ron,
East Coast. Thank you so much. And thank you all for joining us. Thank you all to our live audience here. And we will see you at the next event. Thank you so much.
Thank you.